has done observations confirming an exoplanet. So he actually was one of the first people to know about it.
I don't know if everyone can pick it up. It's actually going through the calibration on the moon at the moment. It's still lifting again.
Yeah. So yeah,
it's up now.
So what we're talking about is the primary mirror. Yeah. I've never seen that before.
Should be lifting again now.
Yeah. So watch very carefully. The primary mirror here
It's just unloaded.
will be
I'll let you
lifting
know.
up again. And it'll only
There
go
it goes
that
now.
far.
Should be lifting now.
Yeah. There it goes. I've never seen that go before. This is cool.
So the mirror is right there.
This silvery kind of thing here, that is the mirror. It's about this thick, 1.5 times. Yeah. It's basically settling in.
Well, basically calibrating everything.
Okay, so yeah, you know more about it than I do, apparently.
What happens with this mirror and the secondary mirror is they actually, when you point them in certain parts of the sky, they flex and bend and everything else. So we actually use pneumatics to actually push it back into shape again. We know what shape it should be, so we actually force it back into shape. But to do that, we've got to know where it is in situ. So then we push it around when we point at something.
And that flexure is why the mirror is so thick, is we want to minimize that flexure so that we don't have as much to correct. Newer telescopes, they're moving a bit more towards thinner mirrors that they can push around more, and they just rely on correcting the shape pneumatically.
One time at the IFA, there was a rumor, I thought you were talking about something we're using to resurface the mirror.
Oh, a vacuum coating chamber. Yes.
Yeah, right.
Yeah, we actually took the mirror out of this telescope. Well, we take off that camera, and then we take off some of the other things around here, and then we lower this part down, and we slide that out of the way. Then we lower this part down, slide that out of the way, and then and that comes with the mirror. The mirror comes down with that. Slide it over, and then there's like a key. What is it called? That goes in the middle.
It's actually just a locking key.
Yeah, but it's this round thing. There's a hole in the mirror. I'll show you the light path in just a second. This comes down through the hole in the mirror, and then it locks in to lift the mirror up from the center. Put it over on a cart, and then we drove it over to the Air Force, just next door, and they put it in a vacuum coating chamber. So they used an acid wash to clean off the old coating. And before they even did that, one of the guys actually put a flashlight underneath the telescope, and you could see holes all over on the mirror where it just worn away. The aluminum had worn basically completely off the mirror in places. And so they washed what was left of the aluminum off, put it in their coating chamber, and evaporated aluminum onto the mirror. And the amount of aluminum on this mirror, I've been meaning to do this calculation, it's probably less than this.
10 microns.
10 microns. That's good thick coating. You know, we use about, in the coating chamber at IFA, we're probably going to be doing about 2,000 angstroms, so 2 microns. So, I mean, 10 microns, you know, that's human hair or less, a little less than human hair.
I have a question. Is that like a rotation technology?
Yeah. So down here, we have some cables down there, a couple computers, but in the pit is the pier, and then there's a flat bearing. You smell the oil smell? You kind of smell the funny smell in here? Okay, that's oil. That's hydraulic oil. There are 2 plates, and we pump oil into those 2 plates, and so the entire telescope is floating on about a 10 micron thick layer of oil. And so it makes a bearing that's very smooth. If we disconnected the motors from this telescope, you would be strong enough and heavy enough to move this telescope around. Okay? And then the bearings here are also hydraulic bearings.
I'm actually not being ignorant, I'm sorry, I'm just, before anyone asks, just to show you it can be done. Telescope.
Oh. He's going to show off in just a minute. You didn't get a chance. Come over here.
Telescope's moving now, that's through an iPhone. So.
Oh my God.
We'll let you ride the telescope. Let him ride the telescope, is that all right? Kids only, sorry adults. Notice I'm on here, I'm still a kid.
The iPhone, that's amazing.
You know you're always welcome, Connor.
So there's an app for that.
Yeah.
It's an off-the-shelf app, actually. It's just the passwords and that get into it a little bit hard.
Yeah. All right.
What's the black screen?
That black screen is used to calibrate the camera.
Wow.
Watch your feet there, won't you?
Hi. You got your spacesuit suit on?
So that every pixel in a CCD camera, in a digital camera, will respond to light a little bit differently. In order to calibrate that, what we do is we take a picture of effectively a blank screen. And so that bar moves, tilt the telescope so it's linking the screen, and then the bar is a light bar, and we scan it in front of the telescope at a constant rate.
Bye, JD.
Yeah. Parents need to be taking pictures of this. Yeah. No. It's not something we let everyone do.
It's just
This is something you will not get to do.
That's one of the reasons why this telescope is actually made. It's not just for science.
You were just trying to get rid of JD, okay? Now you go ahead.
He's easy. I'll just lock him out. You want to come back?
I wasn't expecting it to be like a machine shop in here.
Yeah.
Unfortunately, I haven't got. One of the biggest problems is when I first started here about 5 years ago, is the telescope wasn't running very well, and the only shop that we actually had was over at Maui Observatory. It's just up the road up here. And the biggest problem with that is because you've got to go up and down the bloody hill all the time, just you spend half the time just going backwards and forwards, just to do things. Put the shop in here. You've just got to. You've got to be careful. You've got to keep things clean and everything. It's one of the biggest things, biggest problems with these telescopes is actually swarf and that, metal filings. They're the biggest killer of all because they get blown up into the telescope, they get blown onto the primary mirror and they rust.
Come back around here.
And just make sure everything's cleaned up.
That's where the exoplanets come from.
What's that?
Where the exoplanets come from.
Yeah, somewhat.
Machine shop.
I don't know. I'm not a scientist. So.
All right, we're back. Yes. Mark thought he could get rid of us. Did you get a picture of him with the telescope? Good. Okay.
Just be aware, folks.
So, I was just telling these guys, all these instruments around here are the cameras on the telescope. Now, to an astronomer, this is not a camera. This is a camera and a telescope. The lens, this lens here is the telescope itself. And then the cameras are the sensors that detect the light, the image that the lens projects onto them. And so this telescope, one of the neat things about this telescope is most of the telescopes up on Mauna Kea, say you're observing on Gemini, you want to use the spectrometer.
JD?
Yep.
Sort of over, mate, so
Okay.
be aware.
All right, thank you. We're going to tilt it down to get a better look. So the telescope's over on Mauna Kea. If you're using the spectroscope,
Oh, so that's how it moves.
yeah. So it moves in altitude and azimuth. Isn't it pretty?
For some reason, this makes me want to click on it here.
Amazing.
He wants to ride it.
Okay.
Where you put the saddle?
Yeah. Yeah. No, we don't want to. We don't want to ride the upper part. That's. We'll leave that for Joe Tuss.
Twisting.
There is a rotational. For rotating the back here, there's a kind of a chain that we put the wires in.
It's rotating.
That as the back rotates, it'll kind of wrap around in different ways. It'll kind of unwrap from the outside and wrap onto the inside, or vice versa. And so all the wires from this section kind of go through there, and they come out, and then they get routed down through here, and down below we have just a loop of wire that hangs free, and that loop of wire doesn't tangle.
Twist up.
Just twists up.
Twist it.
Yeah.
So will this do more than 360? Will this continue, or it stops? And then you have to go back the other way?
No, it'll actually go to 520 degrees.
Wow.
Yeah.
At the moment it won't because we've got a bit of a problem with the cache, but normally 520.
So how do you
Yeah.
What's that?
That right there.
I just
screen for calibrating the camera.
VNP,
So
VNC it's called.
okay.
It's just a virtual network.
You see how you know that the picture on my camera,
Control this thing.
You've got to know the address and everything.
there's a little sensor for each point of light on this image. Well, some of those sensors respond to light more and some less.
Virtual network.
So what we want to do is take a picture of a blank white
Yeah, but the
wall
application is actually available.
so that we know which pixels are responding more or less, and we can fix that in the image using a computer. Very CSI.
How many pixels do you have in the camera?
And then once I'm on,
This camera here has about, let's see, it's 4K by 4K, so 16 megapixel approximately. But in normal operational mode, we bin it to 2K by 2K, so you get a 4 megapixel image. The Merope,
They're amazing.
which is the older camera. Is that Merope? Right here, yeah. Okay, this camera is 4 megapixel, but it was binned 2 by 2, so you get a 1 megapixel image. Still a good camera. These are also are science grade cameras. The range of light that they can detect before they get too full or not enough light, that range is much, much larger than your digital camera. This is usually something like an 8-bit. So in other words, you need 8 bits of computer information to store the number for the full range. This is 16-bit, isn't it?
Which one?
Either one.
The 16.
Yeah, 16.
That one's 16 megapixel.
Yeah. So it has a much larger range of numbers that it can use to record because you can read more light. You know, less light to more light. It's got a larger range of actual measurement.
So you mentioned that the dome only won't opens if it's bad weather.
Right.
What is bad weather?
Well, if it's raining, that's the first sign. High humidity, high wind speed. Sometimes they'll also trigger on if the sky is overcast. If it's too cold, it's too hot, I would imagine, but I doubt it ever gets too hot. Just anything that would be a problem for the telescope to operate properly. Or, hail. Hail we call in with raining.
One of the biggest ones is actually ice.
Ice?
Yeah. Because if you think about it, if you've got your enclosure open and everything else and your enclosure iced up, you can't close it. Then you've got a real problem. Because that's what this is for. It's to protect this. So
They won't open if it's like 30